In this video, we're going to focus on reducing agents, such as NaBH4, sodium borohydride, or LiAlH4, lithium aluminum hydride, and even Dibal. So let's begin. Let's say if we have three compounds, a ketone, specifically cyclohexanone, an aldehyde, and a carbocylic acid. We're going to react each of these with sodium borohydride. Now you need to know that NaBH4 is a mild reducing agent. It's less reactive than lithium aluminum hydride, which is very dangerous to handle. NaBH4 reduces aldehydes and ketones and anything that's more reactive than that group. It can also reduce acid chlorides. However, NaBH4 does not reduce carbocylic acids or esters. Lithium aluminum hydride, on the other hand, can reduce carbocylic acids and esters. It can even reduce amides. It's much more powerful. But now let's focus on these three reactions. What are the products of these reactions? So NaBH4, it's going to convert the carbonyl group into an alcohol. So cyclohexanone will be converted into cyclohexanol. Butanol, the aldehyde that we have here, is going to be converted to butanol with an OH. The acid chloride will also be converted to an alcohol. Replace the carbonyl group with an OH, and this group is going to leave. So that's the product of the reaction. Now what you need to know is that if you have an aldehyde or a ketone, sodium borohydride reduces it by the addition of one hydrogen atom. So notice that we have a hydrogen already. Sodium borohydride will add another hydrogen to it. So right now the carbon has two hydrogens. Now when you have an acid chloride, sodium borohydride won't add just one hydrogen to it. It's going to add two hydrogens. So the mechanism for this reaction is a little bit different than for this one. Let's go over it. Let's begin with cyclohexanone. And let's add sodium borohydride to it. In this structure, boron is attached to 4 hydrogen atoms. And boron has a negative formal charge, which is different than partial charge. Now, hydrogen is actually more electronegative than boron. If you look up in Google Images, if you type in the electronegativity chart, you'll see some tables that have hydrogen as 2.1 and boron as 2.0. So hydrogen is slightly more electronegative than boron, so it's going to bear a partial negative charge. And boron is partially positive with respect to hydrogen, even though it has a negative formal charge. Now it's important to understand this because the carbon atom that is attached to the oxygen, it bears a partial positive charge. Since oxygen is more electronegative than it, oxygen bears the partial negative charge. So the hydride ion is attracted to the carbon of the carbonyl. Now the negative formal charge of the boron atom is balanced by the positive charge of the sodium ion. So the hydride ion is going to attack the carbonyl carbon. And then the pi bond is going to break. This is going to produce an alkoxide ion, which is basically an oxygen attached to a carbon atom where the oxygen has a negative charge. Notice that we added one hydrogen. In the next step, we need to protonate the alkoxide ion. You can use water, which can work, but is not as effective as using H3O+. If you add H3O+, this reaction will go to the right with a greater driving force. So this oxygen will grab a hydrogen from the hydronium ion and that's how we can make cyclohexanone. So that's the reduction of a ketone into an alcohol. In organic chemistry, anytime you add a hydrogen, you're reducing the molecule. If you take away a hydrogen, it's oxidation. If you add oxygen, it's oxidation. If you remove oxygen, it's reduction. Now let's go over the acid chloride mechanism, where we have to add two hydrogens to reduce it to an alcohol. Now I'm going to use an R group to represent the carbon structure that we had before. So I'm going to write a generic acid chloride. And it's going to react with sodium borohydride. Now we don't have to worry about the Na plus ion. It's a suspected ion. So just like before, this hydride ion, that's NaBH4, has a partial negative charge. And it's attracted to the partially positive carbon atom. And so we're going to have a nucleophilic addition reaction. So here's the hydrogen that we added, and this oxygen now has a negative charge. So once we form this tetrahedral intermediate, it's going to collapse. Oxygen is going to use this lone pair to reform the double bond, and it's going to kick out the leaving group, the one that's easiest to kick out. Is it easier to remove the R group, the hydrogen, or the chlorine atom? What would you say? If we kick out the R group, we're going to have a carbon with a negative charge, and that's not stable. If we remove hydrogen, we're going to have a hydride ion, which is not stable. But if we remove chlorine, the chloride ion is very stable. So the chlorine atom will be expelled as the chloride ion. So after adding one hydrogen atom, the acid chloride is reduced to an aldehyde. Now we haven't reached the alcohol stage yet, so we can add another hydrogen to it to reduce the aldehyde to an alcohol. Now let's use another borohydride ion to react with this aldehyde. So the mechanism is going to be very similar to the last one. We're going to have a nucleophilic addition reaction. So now we've added two hydrogen atoms, as you can see. This time, we don't have a good leaving group to kick out. We can't really kick out the hydrogen or the R group. So the negative charge is going to remain on the oxygen, and it's going to wait until it receives a proton. So now let's acidify the solution with H3O+. You don't want to mix these two together. Sodium borohydride can react with H3O+, so you want to put them in separate steps. This would be step 1, this is step 2. Now you can mix sodium borohydride with water under highly alkaline conditions, that is under a basic solution where the pH is high. And that under those conditions, sodium borohydride react very slowly with water. Lithium aluminum hydride, on the other hand, will react dangerously with water, so you don't want to mix the two. So it's easier to handle this. And the last step, this is going to grab the hydrogen, and now we have the alcohol. So that's the mechanism of reacting sodium borohydride with an acid chloride. Now let's talk about lithium aluminum hydride. For the most part, this reagent is strong enough to reduce almost anything. It can reduce ketones, aldehydes, acid chlorides, and things that are less reactive. It can reduce carboxylic acids, esters, and even amides. Consider these three compounds. What do you think the product will be for each reaction if we react it with lithium aluminum hydride? Feel free to pause the video and predict a major product. Starting with the ester, lithium aluminum hydride will convert it or reduce it to an alcohol. This group is going to leave, much like the same way that the chloride left in the acid chloride. It's going to reduce the ester by the addition of 2 hydrogen atoms. The carbonyl group is going to convert into an OH. And here are the 2 added hydrogen atoms. As for the carboxylic acid, one of the oxygen atoms will leave, and we're going to have an alcohol on this very carbon. And we're going to add 2 hydrogen atoms to reduce it to the alcohol level. Now, in the case of an amide, the NH2 group will not leave. However, this oxygen will leave. It's going to be replaced with 2 hydrogen atoms. So the amide will be reduced to an amine. And so it's going to look like this. Now the second step, when reacting it with an ester or carboxylic acid, is H3O+. But when you're dealing with an amide, you want the second step to be water as opposed to H3O+. Because if you use H3O+, it can protonate the amine and you're going to get an ammonium ion. It's going to be NH3+ instead of NH2. But now let's go over the mechanism between lithium aluminum hydride and the ester. So I'm going to draw a generic ester using an R group. Like boron, aluminum is going to have 4 hydrogen atoms attached to it. Now aluminum is much less electronegative than boron. The electronegativity value for boron is 2.0. And for hydrogen we said it was 2.1. So that's why hydrogen bear the partial negative charge. In the case of aluminum and hydrogen, aluminum has an electronegativity value of 1.5. And notice that hydrogen is much more electronegative than aluminum. And so hydrogen bears more of a partial negative charge, which means that it's much more reactive. Now the hydride ion is going to attack the carbonyl just as it did before. We're going to have a tetrahedral intermediate. And now we need to decide which group is going to leave. We know the R group is not going to leave, nor will the hydrogen leave. Even though OCH3 is not a great leaving group, compared to hydrogen and the R group, it's a better leaving group. It's better to put a negative charge on an oxygen atom as opposed to a hydrogen atom or a carbon atom. Oxygen is more electronegative than a hydrogen or carbon, so it can stabilize the negative charge better. Now this oxygen is going to use one of its lone pairs to form a double bond, expelling the methoxide ion. So now we have an aldehyde. At this point, we're going to use another aluminum hydride ion to react with the aldehyde. So this is going to attack the carbonyl group. And just like the acid chloride reaction, at this point, after we add the second hydrogen, there's no other good leaving groups. There's nothing to kick out. So at this point, we can add H3O+ to the solution. Once we add H3O+, the oxygen with a negative charge will be protonated. And that's going to give us our alcohol. Even methoxide will receive a hydrogen from the solution, turning into methanol. So going back to our original reaction, Here we have methylbutanoate. In the first step, we used lithium aluminum hydride, and in the second step, we use H3O+. So whenever you have an ester, this bond is going to break, and this is going to leave. Once you acidify the solution, it's going to leave as methanol. And then whatever you have on this side, you need to realize that the carbonyl group is going to be reduced into an OH group by the addition of 2 hydrogen ions, or 2 hydride ions. So that's the reaction for the reduction of an ester into an alcohol using lithium aluminum hydride. Now let's go over the reduction of a carboxylic acid with lithium aluminum hydride. So what do you think is going to happen when we put these two together? What's the first step in the mechanism? So here's a question for you. We know the hydrogen attached to aluminum bears a partial negative charge. Will it attack the carbonyl group as it's been doing before? If the hydride attacks the carbon, it's behaving as a nucleophile. But notice that there is an acidic hydrogen on this carboxylic acid, and it could act as a base. So which one does it prefer? Does it prefer to act as a base or as a nucleophile? It turns out that the hydride ion is going to act as a base. It's going to remove the hydrogen from the carboxylic acid. And as that happens, the oxygen-hydrogen bond will break, a double bond will be formed, and this pi bond is going to break. So this is going to produce a carboxylate ion. Now when two hydrogens get together, that is a hydrogen that has a partial negative charge and a hydrogen that has a partial positive charge, keep in mind oxygen is more electronegative than hydrogen. So if oxygen bears the partial negative charge, hydrogen bears the partial positive charge. When these two opposite hydrogen atoms combine, they convert into hydrogen gas, which will escape and leave the solution. Now at this point, aluminum has only 3 hydrogen atoms attached to it. Before it had 4, and it had a negative formal charge. Now that it has 3, it no longer has this negative formal charge, and the hydrogen atoms attached to it are not as nucleophilic compared to when it had 4. Now what do you think is going to happen at this point? Now the aluminum is a Lewis acid. It has 3 bonds, it has an empty p orbital. So the oxygen with a negative charge can donate a pair of electrons to the aluminum atom in a Lewis acid-base reaction. Whenever an atom donates both electrons to form a covalent bond, the bond that's formed is known as a coordinate covalent bond. And so the structure that we have, I'm going to flip these 2 oxygens. I'm going to put this one to the top. The structure now looks like this. So we have an oxygen bonded to an aluminum atom. Now what do you think is going to happen in the next step? Feel free to pause the video and see if you can determine what's going to happen. Now keep in mind now, aluminum now has 4 bonds, as in the case of LiAlH4, which means that it has a negative formal charge, and therefore the hydrogens attached to it are nucleophilic once more. Now this particular carbon atom has a partial positive charge, which means that this negatively charged hydride ion is attracted to it. Keep in mind, this negative formal charge is not the same as partial charge. Aluminum is less electronegative than oxygen and hydrogen, so therefore aluminum bears a partial positive charge. The negative formal charge is something that we assign to it. The reason why aluminum has a negative formal charge is because aluminum naturally has 3 valence electrons, so it prefers to form 3 bonds, When it forms 3 bonds, it's neutral. But when it has 4 bonds, it has more electrons available to it than it naturally should. So that's why it has a negative formal charge. But it's different from partial charge. Whenever aluminum is bonded to an atom that's more electronegative than itself, it's going to have a positive partial charge, regardless of what the formal charge may be. So just keep that in mind. Now this hydride ion is going to glide towards this carbon atom since it's attracted to it, and it's going to cause the pi bond to break. So we have a tetrahedral intermediate, and aluminum now has 3 bonds. So the R group and the hydrogen, they're not very good leaving groups. But this oxygen is a better leaving group than these two. So what's going to happen now is this oxygen is going to form a double bond and expel this group. Now you might be wondering, if hydrogen is not a good leaving group, how could this leave from the aluminum atom? Now keep this in mind, it's not really completely separating itself from the aluminum. It just sort of moves along the molecule towards the carbon atom. Here, this is going to be completely separated from the molecule, which is different, and that's really a true leaving group. This is more like a rearrangement, so to speak. It moves from one part of the molecule to another part. So it really doesn't separate completely and form a hydride ion, which will be unstable. Now let's focus on what we have after this step. So we have an aldehyde, and we have a side product that looks like this. Now this oxygen can donate a pair of electrons, forming a resonance structure. So the negative charge is shared between the oxygen and the aluminum atom. But we don't have to worry about this part anymore. Let's focus on the aldehyde. So now we're going to reduce the aldehyde to an alcohol. And we know how this is going to work. So we need to use another aluminum hydride ion. And once we have this tetrahedral intermediate, we can acidify the solution with H3O+. And this will give us our final answer. So now we have the alcohol. So that's the mechanism of converting a carboxylic acid into an alcohol using lithium aluminum hydride. Now let's go over the mechanism between an amide and lithium aluminum hydride. So here's a question for you. The hydride ion, will it behave as a nucleophile or as a base? Will the hydride ion attack the carbon as a nucleophile, or will it go for a hydrogen acting as a base? What would you say? Well, to answer this question, we need to draw the resonance structure of the amide. The nitrogen atom can donate a pair of electrons, causing the pi bond to break. And so we're going to get a resonance structure that looks like this. In this resonance structure, notice that nitrogen has 4 bonds. Whenever nitrogen has 4 bonds, it has a positive formal charge. And whenever a hydrogen atom is attached to another atom that has a positive charge, that hydrogen atom is more acidic, which means that these hydrogen atoms are relatively acidic. And so the hydride ion is going to act as a base before it acts as a nucleophile. So it's going to grab one of the hydrogen atoms. These electrons will be used to form a double bond, causing this pi bond to break. So what we're going to have is an oxygen with a negative charge, a double bond between the carbon and the nitrogen atom, and the nitrogen is still going to have a lone pair. Now the aluminum atom now has only 3 hydrogen atoms. So just like before, the aluminum atom is going to act as a Lewis acid, and the oxygen with a negative charge is going to act as a Lewis base. So these two will react. Now what I'm going to do is I'm going to flip these two groups. I want the nitrogen to be facing towards the top. So this is what we now have. Now the carbon has a partial positive charge because nitrogen is more electronegative than carbon. So the hydride is going to attack the carbon much in the same way that it attacks the carbon of a carbonyl group. And then this bond is going to break, giving us this particular intermediate. Now we have a single bond between the carbon atom and the nitrogen atom, and the nitrogen now has 2 lone pairs and a negative charge. Now what's going to happen next? What do you think is going to happen? Just like before with the carboxylic acid, we need to get rid of the oxygen. So what the nitrogen is going to do is going to use one of its lone pairs, form a double bond, and expel the leaving group. So at this point, what we have is an imine. We have a carbon double bonded to a nitrogen atom. So this is called an imine. Now, another aluminum hydride ion is going to react with the imine, much in the same way as this will react with an aldehyde after the addition of one hydrogen atom. So the second hydrogen atom is added, breaking the pi bond, and so now the nitrogen has a negative charge once more. And at this point, there's no more leaving groups to kick out. So the only thing we can do at this point is add H3O+, or rather H2O. If we add H3O+, this is going to convert to an ammonium ion. So let's just use water to get the amine. So the lone pair is going to grab a hydrogen and expel hydroxide. So we have RCH2, and now we have a nitrogen with 2 hydrogen atoms. So we can write NH2. So as you can see, the carbonyl group, the oxygen, was kicked out completely, and it was replaced with 2 hydrogen atoms. So let's say if we have an amide, and if we add lithium aluminum hydride in the first step, and in the second step, if we add, let's say, water, this oxygen will be replaced with 2 hydrogen atoms. The NH2 group will remain. All you need to do is just leave it like this, or you can write it this way. You can show the 2 hydrogen atoms if you want to, but that's the answer. So lithium aluminum hydride can reduce an amide into an amine. Now let's say if we have an acid chloride. Let's say you see a reagent that looks like this on a test. And the temperature is at negative 78 degrees Celsius. What product would you expect to get in this reaction? Now this reagent is called lithium triterbutoxy aluminum hydride. And notice that the aluminum only has one hydrogen, so it can only add one hydrogen to the acid chloride. When you add the first hydrogen, it goes down to the aldehyde level. When you add the second hydrogen, we know that it reduces to the alcohol level. So by having only one hydrogen, this stops at the aldehyde level. So whenever you see an aluminum hydride reagent, but with only one hydrogen atom attached to it, it's a good indication that your answer will be an aldehyde. But now let's show the mechanism for this process. So this is the terbutoxy group. Now there's three of them, and there's only one hydrogen atom. But instead of drawing it like this, I'm just going to write OR, which makes it a lot easier. The aluminum atom has a negative formal charge, and lithium has a positive charge. So the hydride ion is going to attack the carbonyl as usual. The mechanism for this process is not very difficult. We're going to get the tetrahedral intermediate, as always, and the reaction is almost done. This is going to reform the carbonyl group, expelling the Cl leaving group. And so now we have the answer. The reaction stops here. Once you add one hydrogen, that's it. There's no more hydrogen atoms to be added. So it stops at the aldehyde level. In the case of esters, which are much less reactive than acid chlorides are more reactive than ketones and aldehydes, but esters are less reactive than ketones and aldehydes. If you want to convert the ester into an aldehyde, you want to use something called Dibal. And this reaction, you want to carry it out at negative 78 degrees Celsius. What's going to happen is it's going to replace the OCH3 group with a hydrogen. Notice that it only has one hydrogen attached to it. Dibal is basically called diisobutyl aluminum hydride. So what we have is an aluminum atom with one hydrogen atom and two diisobutyl groups, which looks like this. Now notice that the aluminum only has one hydrogen, and so that's why it stops at the aldehyde level. And also, the cold temperature helps. So the hydride attacks the carbon, breaking the pi bond. And so we're going to get this intermediate. Now at negative 78 degrees Celsius, the alkoxide, this oxygen with a negative charge, is not going to kick out the OCH3 group. And so the reaction stops here at negative 78 degrees Celsius. Once all of the hydride donor finishes reacting with all of the ester molecules, then the solution is warmed. So this is going to kick out the OCH3 group, leaving only the aldehyde left over. If you warm it up too early, any unreacted Dibal molecules could reduce the aldehyde. So what you want to do is you want to keep the temperature at negative 78 degrees so it doesn't eliminate the OCH3 group. Dibal won't react with this species. So once all of the Dibal molecules are removed, then you warm it up and it's going to turn into the aldehyde. So if you see any reagent where aluminum only has one hydrogen, the ester in the acid chloride is going to be reduced to the aldehyde level, and it's going to stop there. So that is it for this video. Thanks for watching. Actually, before we end this video, there's one more topic that I would like to cover. So let's say if we have a molecule that looks like this. It has a ketone and an ester functional group. From this molecule, how can we produce the following three compounds? How can we reduce the ketone without reducing the ester? How can we reduce both the ketone and the ester into an alcohol? And how can we reduce only the ester but not the ketone? Now, if you wish to reduce the ketone and the ester, you can accomplish that with lithium aluminum hydride. It will reduce anything that it can get its hands on. Now, if you only want to reduce the ketone and not the ester, use sodium borohydride. It reduces ketones, aldehydes, acid chlorides, but it doesn't reduce esters and carboxylic acids. Now, how can we reduce the ester and not the ketone? If we use lithium aluminum hydride, it will reduce the ketone. And if we use NaBH4, it won't reduce the ester. So what should we do then? In a situation like this, you want to use something called a protectant group. In the first step, you want to add ethylene glycol. It's going to protect the ketone. And then in the second step, you want to use lithium aluminum hydride, which will reduce the ester, but it won't reduce the ketone that is protected. And in the third step, you want to remove the protectant group. So now let's outline the steps of that reaction. So I'm not really going to go over the mechanism for it, just the basic steps. So in the first step, we need to use ethylene glycol, and you can catalyze this reaction by using an acid. Looks like I'm running out of space, so let's put this somewhere else. Now the ester part is going to stay the same. The protecting group, the ethylene glycol, is going to turn the ketone into an acetal. So it's going to look something like this. Now at this point, we can add lithium aluminum hydride. So it's not going to react with the protectant group, but it is going to reduce the ester. So let's move this on top. So now the ester is going to be reduced to an alcohol, and the protectant group will remain the same. And now to remove the protectant group, we need to add water under acidic conditions. And so this is going to convert back to the ketone. And so that's how you can reduce an ester but not a ketone when they're in the same molecule. You have to protect the ketone from lithium aluminum hydride. Once you do that, you can reduce it with this reducing agent and then deprotect it with H2O+, and that's that.